Okay, so today we're doing our specific heat problems, and our equation for specific heat is going to be our energy, which we always measure in joules, so that capital J, equals C, which stands for specific heat, and our unit for that is joules divided by kilograms times Kelvin. Then we have M, which is mass, and that always is going to be in kilograms. And then we have delta T, or delta temperature, which is our change in temperature, and that needs to be in Kelvin. So for this first problem, we have how much energy must be transferred to 200.0 kilograms of water in a bathtub to raise the water's temperature from 25 degrees Celsius to 37 degrees Celsius. So let's start with what we know. We have our mass is equal to 200 kilograms. And that's already in kilograms, so we're good there. We don't need to do any conversions. I know my water's temperature started at 25 degrees Celsius, so that's going to be my initial temperature. And it ended at 37 degrees Celsius, so that's going to be my final temperature. Now we need our delta temperature, or a change in temperature. So to get our change in temperature, we always take our final minus initial. So in this case, we have 37 degrees Celsius minus 25 degrees Celsius, which gives us 12 degrees Celsius. Now, I already said that we want our change in temperature in Kelvin. Luckily for us, the temperature scales for Celsius and for Kelvin match up really nicely. So a change in 1 degree Celsius is the same as changing your temperature by 1 Kelvin. So if my delta T, or my change in temperature, is 12 degrees Celsius, that is the same thing as 12 Kelvin. We don't need to do any other conversions or anything like that. Okay? The last thing we need before we can solve for this is our specific heat. So if you go into your books, there is a chart or a table. It's figure 7 on page 485, and that gives you all of the specific heats that you should need in order to be able to do your problems. So our specific heat of water, because that's what we're dealing with in this problem, is 4,186 joules divided by kilograms times Kelvin. Okay, and we are finding our energy. So I have my equation up at the top of the screen. We can start plugging in numbers now. So we're going to have energy, which we don't know, is equal to C, which is 4,186 joules divided by kilograms times Kelvin, times my mass, which is 200.0 kilograms, times my change in temperature, which was 12 Kelvin. And when I do that on my calculator, I end up getting 10,046,400. Our unit for energy is joules. Okay, but we need to do sig figs. So our 200 grams or 200 kilograms up here has 4, but our initial temperature only has 2 sig figs. Our final temperature only has 2 sig figs. So our answer can only have 2 sig figs. So I'm going to need to do this in scientific notation. So I'm going to do 1.0, because that has 2 sig figs, times 10 to the 1, 2, 3, 4, 5, 6, 7, and move the decimal place over 7 places. So I have 1.0 times 10 to the 7th joules. And that is my answer for this first one. Let's try another one. This time, how much energy is needed to increase the temperature of 755 grams of iron from 283 Kelvin to 403 Kelvin? So again, I know my mass, and that is 755 grams, but I don't want it in grams. I want kilograms, so we need to do a conversion right away. So I'm going grams, getting rid of grams, so grams go on the bottom. Kilograms goes on the top because that's what I'm converting it to. A kilogram is bigger than a gram, so that gets the 1. And there are 1,000 grams in a kilogram. So my grams will cancel out. So my mass in kilograms is 0.755 kilograms. Okay. I also know my initial temperature was 283 Kelvin. Oh, 83, not 33. And my final temperature is 403 Kelvin, which means to get my change in temperature, again, I take my final, which is 403, and I subtract my initial, which is 283, and that gives me 120 Kelvin for my change in temperature, and that's in Kelvin, so we're good there. I'm going to go into my book and find my specific heat for iron this time, which is 449. Well, I don't know what number that is supposed to be. 9 joules divided by kilograms times Kelvin. And now I should be able to solve. So my equation is my energy equals C m delta T. So my energy equals 449 joules divided by kilograms per Kelvin times 0.755 kilograms times my delta T, which was 120 Kelvin. When you do that, you should get 40,679.4 joules. We need to do sig figs. My mass has 3, my initial temperature has 3, my final temperature has 3, my specific heat has 3, so my answer should have 3. So my final answer is going to be 40,700 joules. Okay, and let's try one last one. So what temperature change would copper experience if its mass is 0.455 kilograms and it absorbs 6.33 times 10 to the third joules of energy? So I know my mass, and that is 0.455 kilograms. That one, we're back to kilograms, so we don't have to do any conversions in this problem. It says it absorbs, oh, oops, go back. Okay, it absorbs 6.33 times 10 to the third joules of energy. So my energy equals 6.33 times 10 to the third joules. I can look in my book and figure out the specific heat of copper this time, which is 385 joules divided by kilograms times Kelvin. And it's asking for what temperature. So we're trying to find delta T. We have the same equation we've been using. Energy equals C m delta T. This time I have my energy, so I have 6.33 times 10 to the third joules. I have my specific heat again, so I have 385 joules divided by kilograms times Kelvin. My mass is 0.455 kilograms. And I don't know delta T. So I'm going to first of all multiply these, my 385 and my 0.455 kilograms, just so I have less numbers to deal with. So I'll end up with 6.33 times 10 to the third equals 175.175 times delta T. I'm solving for delta T, so I want to get that alone. Since we're multiplying over here, I'm going to divide both sides by 175.175 divided by 175.175. This will cancel out. That'll be 1. 6.33 times 10 to the third divided by 175.175 is 36.1353. Might keep going a little bit. I'm not sure. That is equal to our delta T. Our unit for temperature is Kelvin. So now we need to do sig figs. We have 3 in our mass. We have 3 in our energy. We have 3 in our specific heat. So my final answer should be 36.1 Kelvin. And there we go.